Hi girls, this is Quantitative Chemistry 2, page 16. And in this short video, we're going to have a look at determining the number of moles of water of crystallization, focusing mostly on the calculations around this area of the topic. But we'll talk briefly through what is the principle behind this calculation, what's the practical behind what we do, and then how do we do the calculations based on it. Because you could be given experimental data in your exam and then asked to work that out, the number of moles of water of crystallization. These calculations are really similar to the experimental calculations that we would have done to determine the empirical formula of a metal oxide that we would have seen earlier in the unit. So it's a really similar method to that. So what you've got in your notes here, first of all, is the general equation for what happens when we heat a hydrated salt, because that's really the principle behind what we're doing. We can determine the number of water of crystallization by taking a hydrated salt. So that's what we're starting with here, the hydrated salt. So you're given the general formula there of your salt, whatever formula that might be. It could be copper sulfate, magnesium sulfate, iron sulfate, lots of different things. Bonded with a certain number of water molecules, where N or sometimes X represents the number of water molecules. So if we take our hydrated salt and we heat that, we will change to the anhydrous salt. So we will essentially remove the water, and that water is then going to be removed as steam, because when we heat the hydrated salt, the water will evaporate. Okay, and we're left with the anhydrous salt, which will often be like a white powder, and the water will have been removed. So essentially what we'll get then, we'll be able to measure the mass of the hydrated salt at the start of the experiment. We'll be able to measure the mass of the anhydrous salt at the end of the experiment after we've removed all the water. And we'll be able to use that to get the ratio of our anhydrous salt to water, and that gives us our formula. So you can see a specific example has been written for you here of copper sulfate. So you can see copper sulfate bonded to 5 molecules of water. If we heat that, then you can see the anhydrous version of the salt, so that's without water, and our 5 water molecules have been removed and will escape as a colourless gas. So in this experiment, the mass will decrease, and the difference between the mass of the hydrated and the anhydrous salt will be the mass of our water. I'm going to skip on to the next page and have a look at the practical method. So this is just a summary of the practical method, and just we've talked about that already, that essentially what we want to do is measure our solid, which will be our hydrated salt to start with, in a container, and that needs to be an open container so that the water can evaporate off. So that might be an evaporating basin or an open crucible. We then will heat for a few minutes, cool, and then reweigh, and repeat step 2. So keep heating and reweighing until we get a constant mass, until the mass doesn't change. And at that point, what we'll be left with is the anhydrous salt. So what we want to focus on in this video is how that would look in a calculation. So these calculations could be presented to you in your exam, and they would give you values of masses, and you have to interpret that to determine how many waters of crystallization do we have. So if you look over at the next page, here's the steps to follow when you're calculating the degree of hydration. And this is very similar to the method that we looked at for determining the empirical formula of a metal oxide using experimental data. That time we were heating and the mass was increasing because we were gaining oxygen. But again, we heated until we gained constant mass. But here we will see that the mass will decrease because we're driving off the water. So essentially from these calculations, we'll need 3 values. We'll need the mass of the hydrated salt, the mass of the anhydrous salt, and the mass of the water. How we get the mass of the hydrated salt is we take the mass at the start, and that will be probably with a container, but we can take the mass of that away. Mass of the anhydrous will be at the end of the experiment, so we could put here, that's at the start. That's at the end after heating. And the mass of the water equals the mass of the hydrated, take away the mass of the anhydrous. So that is step number 1, calculate the mass of water in the hydrated salt by subtracting the mass of the anhydrous salt following heating from the mass of the hydrated salt. Then we want to convert masses into moles. So we need, at that point, we need the moles of the anhydrous salt and we need the moles of the water. At that point, the mass of the hydrated doesn't actually matter because we're just putting these two values in a ratio together. Calculate the mole ratio by dividing by the smallest mole value. That's similar to what we did with empirical formula. And if your mole ratio is a decimal, multiply it all by the same number to get an integer value. That's not all that common with these ones. Generally, we'll have the equivalent of a ratio of 1 of our anhydrous salt and then to a certain number of water molecules, 1 or more. So let's have a look at two worked examples, and you'll find, again, these are really similar to the ones that we did with determining the empirical formula from experimental data. So it says here, in an experiment to find the mass of water of crystallization in hydrated magnesium sulfate, the following results were obtained. And what we're essentially trying to do in this is determine the value of X. How many water molecules are there for every 1 molecule of magnesium sulfate? So what I'm going to do, a bit like we did with empirical formula, is I'm going to put numbers beside the important values. So we will need to use the mass of the empty evaporating basin. We will need to use the mass of the evaporating basin and hydrated magnesium sulfate, because that's going to give us the mass of the hydrated salt. And then we will need the mass after heating to constant mass. That's the last mass. Mass after heating for 13 minutes. What do we have in there? That's the evaporating basin plus the anhydrous salt. So have a think about what is each of these values representing. Okay, so let's have a look at the question. And some of these are led to slightly differently. Some of them will kind of skip the step of working out the hydrated salt. So let's have a look at these questions the way they've been guided to us. Make sure that at the end of every part of the question that you have units with your answer. So calculate the mass of the anhydrous magnesium sulfate. So how are we going to work that out from our values? Well, if you have a look at what value 3 is, it's the evaporating basin plus anhydrous salt. So we're going to take value 3 and take away value 1. So for this example, that will be 13.33 minus 12.73, and that will equal 0.60 grams. I'm going to leave that to 2 decimal places because all our other masses are to 2 decimal places. Okay, so we're just taking away the mass of the empty evaporating basin to get us the mass of the anhydrous salt. Let's go over to the next part. So the next part says calculate the number of moles of the anhydrous magnesium sulfate. So we're going to use our equation moles, or N, equals mass over RFM. Let's work out what the RFM is first of all. So the RFM, that's of magnesium sulfate. You can see in the question that is just MgSO4. So you don't need to work out the formula that's been given to you in the question. So 1 magnesium is 24, 1 sulfur is 32, and then you've got 4 times 16 for your oxygens. And that should work out as 120. Do this along in your calculator with me so that you can see these values coming out. And then we need to work out the moles. So we're taking the mass over RFM. The mass in the previous part of the question that we just worked out was 0.60 divided by 120. And put that in your calculator. You may see that it comes out as standard form. I'm probably going to write it just as a normal decimal, so 0.005 moles. It may come out as 5 times 10 to the minus 3, which you can write down, but it's just a wee bit more difficult to use in your calculator later on. Then you want to calculate the mass of the water of crystallization removed. What I've put on the screen, again, just briefly, is our values again, but just flick back to your previous page to have a look at that. How could we calculate that directly? Well, if you think what is happening between value 2 and value 3 is that we're heating. You can write this in the previous page if you want to. You're essentially removing the water. Because think about what value 2 is. That's evaporating basin plus hydrated magnesium sulfate. Value 3 is evaporating basin plus the anhydrous salt. So the difference between the two is going to be the water that has been removed. So you can actually do this directly by doing value 2 minus value 3. So let's have a wee look at that, and then I'll show you another way to do it. It depends what way you think you would find easier, understand more, or use in the future. Sorry, my pen's being a bit annoying. So that's 13.96 minus 13.33. Put that into your calculator, and you should find that that gives you 0.63 grams. So that is your answer. Or what you can think about is, we know that the mass of the water is the hydrated minus the anhydrous. So we've already got the mass of the anhydrous. So what we could work out is the mass of the hydrated salt. So this is just really doing it in 2 steps rather than 1. So that would be value 2 minus value 1. That would be 13.96 minus 12.73. You're just taking away the mass of the evaporating basin. And that will give you 1.23 grams. Mass of water then is hydrated minus anhydrous, which would give you 1.23 that we've just worked out, minus 0.60 grams. That's our mass of our anhydrous, and that would give you 0.63 grams. So either's fine. You can say it gives you the same answer, but just whatever way that you find would be more helpful. So I'll just get rid of our mass values again and move on to part D. Calculate the moles of water of crystallization removed. That's moles, or N equals mass over RFM. Mass is 0.63 grams. The RFM of water is 18. Remember, that's H2O, so 2 from your hydrogen plus 16 from your oxygen is 18. And put that into your calculator with me, and that comes out as 0.035 moles. And what we're doing at this point is finding X in the formula, and we do that by measuring a mole ratio, finding a mole ratio of magnesium sulfate, the anhydrous, to the water. And if you want to put that in, it's always going to be your anhydrous moles to your moles of water. Okay, so let's have a look, and this is so similar, pretty much identical to what we were doing with the empirical formula ratios. So the anhydrous salt, we said we got let me write the formula in here. That's MgSO4, and that's to water. So whatever number we get as our ratio for water, that will be our number of water of crystallization. Moles of magnesium sulfate, we worked out as 0.005, or 5 times 10 to the minus 3, whatever way you've written that as. Moles of water, we've just worked out as 0.035. How do we get our mole ratio? We'll go back to your method if you can't remember, but we said we divide by the smallest number of moles. What is that in this case? Well, it should actually always be the moles of your anhydrous salt if you've done the calculation correctly. So we are, and that is the case here, that we're going to divide by 0.005. What does that give us? Well, you're dividing by itself for magnesium sulfate, so that gives you 1. And then 0.035 divided by 0.005 is 7. Just use your calculator for that. And what that means is that there's 7 water molecules for every 1 molecule of magnesium sulfate. So that means essentially X is equal to 7. The final formula of your salt is MgSO4.7H2O. Question asks you what is the value of X. You could just write X equals 7. So you can see from that point on, it's really similar to our empirical formula calculations. Okay girls, I'm going to do one more example with you, and then I'm going to get you trying a few yourself. So this worked example 2, you're not given quite as much experimental data, you're not given like the mass of the evaporating basin, so this is in some ways a little bit more straightforward. So it says here that given that 4 grams of your hydrated produces 2.56 grams of anhydrous copper sulfate, on heating, find the value of N. Now they've changed X to N, but that doesn't matter. We're trying to find the number of waters of crystallization in this. So we can just work with the direct values they've given us. So the hydrated salt, the mass is 4.0 grams. The anhydrous salt is 2.56 grams. So always think these are, they wouldn't have given you the steps in this question, but those are the 3 values you need: hydrated, anhydrous, and water. So it's 2.56 grams. Value of the water lost is going to be 4.0 minus 2.56. Put that into your calculator and it gives you 1.44 grams. And then the two values that we really need are the mass of the anhydrous and the mass of the water. Okay, so what is our anhydrous salt this time? It's copper sulfate, CuSO4. It's always a ratio of the anhydrous salt to the ratio of water. So that's H2O. So what is the mass of each? The mass of your anhydrous salt is 2.56. Make sure you use the right value there. The mass of water is 1.44 grams. The RFM of each of those, the RFM, relative atomic mass of copper, is 64, plus your 32 from sulfur, plus your 4 oxygens, gives you an RFM of 160. And then for water, that gives you an RFM of 18. How do we work out our moles then? We're doing mass over RFM. So for copper sulfate, that's 2.56 divided by 160. And that will give you 0.016. So again, do this along in your calculator with me if you can. For water then, that's 1.44 grams divided by 18. And that is 0.08 moles. How do we work out the mole ratio? We always divide by the smallest number of moles. That in this case is copper sulfate. So divided by 0.016. So divide both of those numbers by that. So that's going to give us 1 for our anhydrous salt. And then for water, that gives us 5. So the formula is just then CuSO4.5H2O. And again, the question asks you, what is the value of N? So your final answer would actually be N equals 5. So if they ask you for the formula, write the full formula out, remembering your dot for the water of crystallization being bonded. If they just ask you for the number of water of crystallization, then it's just a simple number. So what I would like you to do is have a wee go at exercise 4. And you'll need to do this on file paper, and again, keep the file paper with your unit, keep your notes nice and organised. You can see examples like 1, 2 and 3 here. They haven't given you a load of experimental data, but they have given you the mass of the hydrated and the anhydrous, and you're just working through a bit like worked example 2 there. So 1, 2 and 3 are very like worked example 2. If you look at worked example example 4 and 5, that will be more like worked example 1, where you're working with the values of the evaporating basin and taking those away and so on. Number 6 I want to mention briefly because it is a little bit different. It's easier actually to treat that as a reacting mass calculation. So what you'll need to do with question 6 is write an equation for what happens when you heat your hydrated cobalt chloride with 6 waters. Just be careful, cobalt is CO and it's not carbon and oxygen, so be careful about that when you're getting your RFM. So what you need to do is write an equation for that. So write equation, and then what I'm going to say here is see page 16 to help you with that. So on page 16 you'll see the equation written for copper sulfate, dehydrating as such, the water being removed, but you just change this for cobalt chloride. So the start of your equation will be COCl2.6H2O, and then an arrow, and then think about what you form. Essentially just it's the two things separated, cobalt chloride plus your 6 waters. Then you've been given the mass of the hydrated cobalt chloride as 3.57 grams. You essentially then just work out the moles of that and bring it over to the moles of your anhydrous salt, and then use mass equals N times RFM to work out the mass. So think of that more as a reacting mass type calculation. Give it a go, and if you're really not sure, just try and get to some point with it. And if you're not sure, send me an email and I can help you with that. Send me a picture of what you've done so far. And then number 7 is a bit like just worked example 2 again. There are some extra questions there if you'd like a bit of extra practice, but as long as you have 1 to 7 done for our next lesson, then that's perfect. Okay, so hope you got on okay with that, and just email me if there's any issues.